Exam 1, problem 2. In this one, we have a net electric field, 100 newtons per coulomb, directed downward on the surface of Mars. We want to know the magnitude and sign of the excess charge, and we're going to say, model that out, part A, right? That the electric field equals kq over the radius of Mars squared, right? It's as if there's a point charge at the center of Mars that is giving us this electric field. Well, and we're going to be interested in Q, right? So Q is just E R squared over K. Now, the electric field is pointing downward, which is, I'm going to write it as minus 100 newtons per coulomb because it's pointing downwards. The radius of Mars I have here 3.4 times, let me do this, 3.4 times 10 to the 6th meters, right, squared. And then we have to divide by K, 8.99 times 10 to the 9th newtons meter squared per coulomb squared. All right. So what does this all end up being? We have minus 100 times 3.4 e to the 6th squared divided by k, and so we get a charge of minus 1.29 times 10 to the 5th coulombs. Now, part B we've already answered, in that I said, if we have a charge that's positive, the electric field is going to point away from it. So I made the charge the electric field which is pointing down negative, and things worked out so that we now know that this charge is negative. All right, part B. What acceleration would the field produce on a free electron near Mars' surface? All right, so we know force equals mass times acceleration. We also know in this instance that force is charge on the electron times the E field. All right, so what is the charge on the electron? We have Q is minus 1.6 times 10 to the minus 19 coulombs. We have the mass of the electron, which is 9 times 10 to the minus 31 kilograms. All right, we have Q, we have the mass, we have electric field, we're after the acceleration. Well, we know mass times acceleration equals Q times E because the force accelerating it is the force of the electric field. The acceleration then is QE over M, which is minus 1.6, 10 to the minus 19 coulombs times minus 100 newtons per coulomb divided by the divided by the mass of the electron. 9 times 10 to the minus 31 kilograms. All right. Well, so let's go figure out what the acceleration to the electric field is. It is minus 1.6 e minus 19 times minus 100 divided by 9e minus 31. So just looking to see if that makes sense, because this would be like 10 to the minus 17 over 10 to the 31. Okay. All right. So 1.8 times 10 to the 13th. Meters per second squared. Right? 1.6 charge, electric field, divided by the mass, and there you have it. All right, part C, what mass object with a single extra electron will have its weight supported by this field? So, in part C, we're looking at the exact same equation, right? We're talking about the force being the same in that, oh, and this, by the way, this acceleration is upward because of our sign convention, right? So we're talking about the force being the same. So the force is still QE, but now we have a different mass. So we have M and acceleration. We want the acceleration to be equal to the gravitational acceleration on Mars, right? And QE is the same. And so what we're looking for is what is the mass of an object that's supported by this right? Now, Mars is 3.8 meters per second squared. So we have minus 1.6 times 10 to the minus 19 coulombs times, see if I can correct that mistake, coulombs times minus 100 newtons per coulomb, right, all divided by 3.8 times 10, 3.8, not times anything, meters per second squared, right? So what would be the mass? So minus 1.6 E minus 19 times minus 100 divided by 3.8. And we get 4.21 times 10 to the minus 18 kilograms. 4.21 times 10 to the minus 18 kilograms. And that's it for part C. All right, done with problem 2.